Hello and welcome. This is Bhaskar from Pharma Growth Hub. In today's video, we are going to discuss about adjustment of chromatographic condition as per USP General Chapter 621. In this video, we are going to discuss about adjustment in gradient time if you are using liquid chromatography in gradient elution mode. In the last video, we discussed about adjustment in column parameter. So in case if you are looking for the adjustment in column parameter information, please watch my previous video. So let us discuss about adjustment in gradient time in this video. So change in column dimensions, that is column volume, impacts the gradient volume which controls selectivity. So in case if you are making a change into the column dimensions and if the length of the column get changed, the column volume will also get changed. Now this change in the column volume, maybe decrease or increase, have the impact onto the gradient volume too. And this gradient volume may be a critical in terms of achieving selectivity, in terms of achieving resolution, in terms of achieving the retention time. So for that reason, we need to understand the impact of change in the column dimension onto the gradient volume. Gradients are adjusted to the column volume by changing the gradient volume in proportion to the column volume. So we need to change the gradient time. We need to change the gradient time in case if there is a change in column volume, because this column volume brings the significant changes into the chromatographic characteristics. So how to adjust the gradient volume? So the gradient volume is equal to gradient time into flow rate, which can be adjusted by adjusting gradient time. So for changing the gradient volume, we need to change the gradient time or even the flow rate also. So by changing the gradient time and flow rate, our gradient volume can get changed. So gradient time for each gradient segment needs to be adjusted to maintain a constant ratio of gradient volume to the column volume. So in case if you have a multiple gradient segment, then all this multiple gradient segment, I mean the gradient time for all this multiple gradient segment needs to be changed. And we are going to talk about this change with the help of example. So please keep watching. So first understand the how the new gradient time can be calculated. And this is the calculation formula. So the TG2 stands for the new gradient time. And let us understand the meaning of each and every term. So F1 stands for flow rate indicated in the monograph method. F2 is what? Your adjusted flow rate, because you have changed the column dimension and now you have made the change into the flow rate, that is the adjusted flow rate. L1 stands for length of the column indicated in the monograph method. L2 stands for length of the column used. Now you have used another proposed column, so the length of that proposed column is L2. DC1 stands for internal diameter of the column indicated in the monograph, and DC2 it's internal diameter of the column used, which is proposed by you. So changing the gradient time is the three-step process. Let us understand all these steps. So the step 1 stands for adjust the column length and particle size according to L by dp. L stands for column length and dp stands for the particle size. The step 2, adjust the flow rate for changes in particle size and column diameter. And step 3 indicates adjust the gradient time for each segment for changes in column length, diameter and the flow rate. And let us understand this all stages with the help of example. Now this is the example. The original condition and the adjusted condition. So what we thought of doing change is the adjusted condition. And the original condition is what? The condition given into a monograph. So the column length as per the method in a monograph is 150 mm. And you have proposed the change in the column length to 100 mm. The column diameter in millimeter as per the monograph method is 4.6 mm. And you have proposed the column diameter of 2.1 mm. The particle size as per the monograph method is 5 micron and you have adjusted the particle size to 3 micron. So calculate the L by dp first. Understand the L by dp ratio for the original condition as well as the adjusted condition. So L by dp means length divided by particle size, which is 150 divided by 5 micron in this case becomes 30. And for the adjusted condition, the L by dp becomes 33.3. So I will not explain the further figures, but let me make you understand what is the situation in the change in column length and the diameter. Whether this change is accepted according to USP General Chapter 621. So first confirm whether the length and particle size of the proposed column follow L by dp rule. So what is the L by dp rule? So L by dp with proposed length and column with the proposed length and the particle size must be within minus 25% to plus 50% with respect to its original value. Original means the monograph value. So you have the column length, you have the particle size. As per the monograph method, you have made certain changes into the column length and particle size. So the value of proposed L by dp should fall in the range of minus 25% to plus 50% with respect to L by dp of the original column length and original particle size. So calculate L by dp for original conditions 30 and for adjusted condition 33.3. Remember that column length is 150 mm and particle size is 5 micron according to the original condition. And for the adjusted condition, the column length is 100 millimeter and particle size is 3 micron and hence the L by dp for adjusted condition is 33.3. The next step is confirm the acceptability. So understand the percent difference now. So original L by dp is 30 is equal to 100% and proposed L by dp is 33.3 is equal to X%. So we need to calculate the relative percent of L by dp for the proposed change and X is equal to substitute the values and you will find that the X% is equal to 111%. So the L by dp ratio with the proposed length and proposed particle size is 11% higher as compared to the original L by dp ratio. So is it acceptable? Is it acceptable? It meets the requirement because still it falls the window of minus 25% to plus 50%, and hence the proposed change into the column length, the proposed change into the particle size should be accepted as per USP General Chapter 621. Step number 2. Calculate the flow rate with proposed column dimension. Now, as the column dimension is changed, you cannot use the original flow rate to maintain the similar kind of linear velocity. And let us understand now what is the new flow rate. So F2 is new flow rate, and this is the calculation formula. Understand the meaning of each and every term. So F1 stands for flow rate indicated in the monograph method. F2 indicates the adjusted flow rate. DC1 indicates internal diameter of the column indicated in the monograph. DC stands for internal diameter of the column used. DP1 stands for particle size indicated in the monograph method column, and DP2 stands for the particle size of the column used or the proposed. Let us understand the F2 value now. So assume that the F1 is equal to 2 ml per minute. DC1 is equal to 4.6 mm, DC2 is equal to 2.1 mm, DP1 is equal to 5 micron, and DP2 is equal to 3 micron. I'm just you know collecting the details from this particular table, right? So I have everything over here, and I have just collected the information one more time in this box. So I have F1, I have DC1, DC2, DP1, DP2, and hence I can be able to calculate F2. So what is the new F2 I got? Substitute the value of all these factors, and I will found that, okay, so yeah, a small correction is needed. Okay, it looks far better. So the new F2 is 0.7 ml per minute, right? With the proposed change into the column dimension, the new F2 value is 0.7 ml per minute. Look at here. Adjusted condition, the flow rate is 0.7 ml per minute. Now I need to calculate the third step is the calculation of new gradient time, that is TG2. And this is the calculation formula for the new gradient time. TG2 can be calculated once you understand the TG1, F1, F2, and L2 DC2 and L1 DC1. Let us understand the meaning of each and every term over here. The TG1 stands for original gradient time. F1 stands for flow rate indicated in the monograph. F2 stands for adjusted flow rate. L1 stands for length of the column indicated in the monograph. L2 stands for length of the column used. DC1 stands for internal diameter of the column indicated in the monograph, and DC2 is the internal diameter of the column used. So let us understand the all the values. See, we have all the values now except TG1. We will have F1, F2, L1, L2, DC1 and DC2. So these are the values. F1 is 2 ml, F2 is 0.7 ml. We just calculated F2, right? I hope you remember that. L1 is 150, original length of the column. L2 is 100 mm, the proposed column length. DC1 is the particle size of the sorry, not the particle size, but the internal diameter of the monograph column. And DC2 is what? The internal diameter of the proposed column, which is 2.1 mm. Now substitute the values in the calculation formula, and what we found at the end, the TG2, the proposed new gradient time, is equivalent to zero point 0.4 TG1. zero point 0.4 TG1. Let us understand now with the help of example. So define the new gradient program and gradient time. And here is the gradient program. So original gradient program is what? Your TZ1 stands for the original gradient time. and this is the percent B. Hmm? So at 0 minute percent B is 30%, at 3 minute percent B is 30%, at 13 minute percent B is 70%, and at 16 minute percent B is again 30%. So what is the next step now? We need to understand if the column dimension is getting changed, if the flow rate is getting changed, what is my proposed gradient time? And here is the details now. So we need to adjust the gradient program, and let me show you how this can be done. So let us look now the adjusted gradient program. That means you want to calculate the new gradient time. See, I hope you remember that the Tg2 is equal to zero point 0.4 times Tg1. Tg2 is our new adjusted gradient time and Tg1 is our original gradient time. And if you want to see where I have done this calculation, it is here. Tg2 is equal to zero point 0.4 times of Tg1. So if I have the value for Tg1, I can easily calculate the value for Tg2. So why Tg2? The Tg2 is the new gradient time with the proposed column dimensions, with the proposed column length, with the proposed column inner diameter, and the flow rate. So let us have the calculation. So Tg2 is equal to, for first, if it is what, how much? It is 0 minute. So 0 into zero point 0.4 becomes again 0. I'm not going to change percent %B. It is going to remain one and the same. I will get the similar performance just by changing the gradient time. The second point is 3 minute. Hmm? The second point is 3 minute. So the new gradient time will be 3 into zero point 0.4, which is 1.2 minute. The next is 13 minutes. So 13 into zero point 0.4. I'm multiplying zero point 0.4 to get the Tg2. So 13 into zero point 0.4 is equal to 5.2 minutes. And the last one is 16 minutes. So 16 into zero point 0.4 is 6.4 minute. So now my new gradient program will be 0 minute 30%, 1.2 minute 30%, 5.2 minute 70%, 6.4 minute 30%. Now this gradient program needs to be changed to achieve similar kind of performance as equal to the original gradient program. Now why this change? Because we have changed the column dimension, particle size and the flow rate. So this calculation is very important. And once you understand this calculation, you will be able to identify the new gradient program in your case. So I hope you must have liked the content of the video, and in case if you want to receive the very useful and informative content like this one, you can join the WhatsApp group of the Pharma Growth Hub. So to join the WhatsApp group of the Pharma Growth Hub, click the link given in the description and you will receive a very useful and informative content immediately once it gets available. Thank you so much.